All right. Okay, so we've had a series of cancellations, of last-minute cancellations, so I am a sub for one of them. So in any case, I think I'm here to talk about a conjecture. It's not really a theorem, and it's a conjecture that I haven't done any work. So before I forget, I'll mention some people that actually did some work on this conjecture. But I think this conjecture might be at the heart of some of you, so you might actually like the problem that is being posed. So it's a conjecture about, so I need to talk about three things. I need to talk about finite groups, because it's a conjecture about an action of the group M24, Mathew's M24, and Mathew's is that Mathiew, not how it was translated in the program. It's an action, so I guess I should say complex manifolds. Because it's about the action of M24 on certain bundles or certain cohomologies of bundles on K3 surfaces. And finally, I need to talk about infinite dimensional Lie algebras, because this conjecture involves this action of M24 commuting with an action of the n equals 4 superconformal algebra, which Minoru introduced yesterday. All right, so since I'm going to spend most of my talk talking about just this, giving a feeling as to what this group M24 is, and some of you already might know what that group is, you might be bored. So let me just give you a little tip of what this conjecture would say, which is that. So that slide is going to stay there for a while. If you know what M24 is, you can spend your time trying to prove that conjecture there. That would be an interesting article already. All right, so I want to start with a baby version of what M24 is. So let's think of this. This part of the board is going to be CP1. And here you have a tessellation of CP1, which is by this dodecahedron. And you learn early on, say, grad school, probably earlier, that the group of symmetries of this is the group A5. So let's put this in this board. A5, thinking inside of SO3 as the group of rotations in R3 that preserve this dodecahedron, that's A5. And what are the 5 things that are being permuted? This is as follows. So in order to find what are the 5 things that this A5 is permuting, you look at colorings of the 20 vertices with 5 colors. And the condition is that in each phase, you have the 5 colors. Right? So here there's one coloring. So I marked the 4 blue colors, 4 blue vertices, and you get the other ones rotating this. Right? There's essentially 2 different ways of coloring the dodecahedron that way. Either one would do. And now, what is A5? Well, A5 is permuting those 5 tetrahedra that you get inside of the dodecahedron. Right? For each color, you have 4 vertices. That gives you a tetrahedron. And A5 is permuting those. All right, so having said so I guess I should also say, so this A5, which is PSL2 over F5, instead of viewing this inside of SO3, now I'm going to enlarge this group inside of S12. So S12 by permuting the 12 faces of the dodecahedron. And to enlarge this, I'm going to use a non-geometric symmetry of the dodecahedron, which is, well, so this is a failed attempt to describe what I wanted to do, which is the following. On each of the 4 blue vertices, we're going to break the dodecahedron in 4 sets. Right? Each set has the 3 faces that are adjacent to that blue vertex. And, well, we broke it. Now you rotate these 3 faces, right, 120 degrees. You do this on the 4 vertices, and then you glue back your dodecahedron. Right? So this gave you a Z by 3Z inside of S12 as well. Right? This operation, if you do it 3 times, you certainly go back to the identity. So the group generated by PSL2 over F5, this A5, and Z divided by Z, 3Z, this group is called M12. Right? This is generated by these 2 subgroups of S12. So symmetries of the dodecahedron is M12, and M12 acts on 12, on the set with 12 elements, which are the faces of the dodecahedron. M12 is a simple group, a 5-transitive simple group that Mathiew was studying transitive groups, multiply transitive groups, and well, he sort of like found them all the simple ones. Okay, so that's the baby version of what the Matthew's group is. So now I want to give you a feeling along those lines of what M24 is. But now instead of having this genus 0 curve, now we're going to need a genus, well, let's go to, I'm going to need a quartic in P2. But that one is much harder to draw than the dodecahedron, so I brought a drawing already. Oh, that was to show that people do learn early what a dodecahedron is. Yeah, I guess Maggie learned in elementary, in preschool. All right, so that's going to be the analog, not of the dodecahedron. So here, I'm going to have the icosahedron. So this is going to be the analog of the icosahedron. And I'll explain why in a second. Right, so that there is a tessellation of a curve inside of CP2. So we take, inside of CP2, we take the zeros of the following polynomial. X cubed is equal to 0, I guess. This is called the Klein's quartic. And this curve has the group PSL2 over F7, which is a simple group, which is also GL3 over F2. Well, I guess isomorphic. As group of automorphisms. Actually, Klein, in the 1885, I think is the right date, he found a representation of this group of dimension 3. And this polynomial here is the unique invariant of order of degree 4. So that's why this curve has this set of automorphisms. Now, I'm trying to give you a tessellation of this curve. And now it's much more complicated. We're gonna do this with a bunch of, so that's the figure, and I want to tell you how to build that figure at least. So we're gonna use 4 pieces like this. So this is a prism that has 2 triangular faces and 3 square faces, and 6 pieces like this. This is a prism that has 2 square faces and 4 rectangular ones. You put the 4 pieces, which are these triangular ones, in the vertices of a tetrahedron. So these are the 4 guys. And then you use these 6 ones in the edges of that tetrahedron to join along the square faces. So I'm going to glue this square face here to this square face there. So that's what we're doing. But not only gluing like this, but also as I am gluing it this way, I am twisting it. So it's not just a straight gluing. That's why this guy here goes in the back, and this guy that is here in the front goes here. Right? So those are the ones that are joined. Moreover, since we want to have, I mean, if I do it this way, then I have 2 types of faces in this polyhedron. I have some triangles, and I have some rectangles. So in order to get rid of that, what you do is you triangulate this. You divide each of these ones in 2. Right? And now what? I should have done this here. I should see an extra line here. And I have now 2 triangles there instead of a rectangle. And that's the figure that is there. So let's start counting faces, vertices, and edges there. Right? So it's easy to count vertices here. So, well, I have 3 on top, 3 on the bottom is 6 times 4 is 24, and that's it. All of the other vertices on these pieces, I already glued them to vertices of those other pieces. So I have 24 vertices. Faces is also easy. Well, I have, well, let's see. I right? There's no more square faces. For every square face, I already glued something to it, so I am only left with triangles. And I have 2 times 4, which is 8, plus, and here I have, well, I have the 4 times 2 is 8 times 6. So it's 8 times 6, which is 56. And edges, you can guess it, right? The genus of this curve is 2. I think I'm saying something very, very wrong. The genus of that curve is 3. Otherwise, the count would be very wrong. So we have these 2 guys add up to 80. So edges should be 84. And luckily, the genus is 3. All right. So I said this would be the analog of the icosahedron. So let me tell you what is the analog of the dodecahedron, actually. And the analog of the dodecahedron would be the dual polyhedron to that. So I'll have, well, the dual would be, so the Klein's dual would be 24 faces and 56 vertices. And still our 84 edges. All right. So now let's look at this. Each of these vertices here you can count. Well, you can see it more clearly there. From each of these vertices, there's 7 edges that go out. This means that in this polytope, each face here is an heptagon. And now we have the analog of A5, which is now, instead of PSL2 over F5, is now PSL2 over F7. It acts, instead of in S12, I'm thinking of this guy inside of S24, permuting the faces of this polytope. And now I'm going to enlarge this in the same way that we did that. So we play the following game. We use 7 colors for the 24 edges. So this means, well, I guess 84 divided by 7 is 12. So we have, for each color, we have 12 edges that have that color. And the rule is that, of course, that each face has the 7th color. Each face has 7 edges, and I want them to have the 7 colors.
Well, you were coloring vertices.
Yeah, now I'm coloring edges. Yeah, that's right. This is a different story. But now the non-geometric thing, so the non-geometric symmetry of this polyhedron would be the following. Whenever you see an edge which is blue, just flip the 2 faces adjacent to that edge, right? So that's going to give you a Z divided by 2Z inside of S24, permutations of these 24 faces, and we still have our P SL2 over F7 inside of that group, and the group generated by these 2 is Mathew's M24. And I like this description because for my purpose it's going to be nice because it involves Klein's quartic, and also it says that all I need inside of S24 to get M24, besides the symmetries of the Klein's quartic, is an involution. I just need to find this extra involution, and I can get M24. All right. So that's about it for finite groups, and I'm more or less fine. All right, so let's move on to the part on geometry. So, oops, that's bad. Let's keep that slide there. All right, so let me give you a definition on where I want this group to act. So definition, this is going to be my working definition. A K3 surface is a compact connected, I'm very bad, simply connected Kähler manifold dimension 2 times 2, real dimension 2 times 2, such that, and choose any of the following as your equivalent condition. Either C1 of the complex tangent bundle is 0, or there exists a holomorphic volume form, or the holonomy of your manifold is SU2, or the holonomy of your manifold is SP1, or the manifold is Ricci flat. Let me add that on this side. Let me put it here. Or the manifold is Ricci flat. Or the manifold is hyperkähler. Or the manifold is holomorphic symplectic. I mean, some of them are obviously equivalent. For example, these two, I guess. So that's going to be my definition, my working definition of a K3 surface. And you might be interested in them for different reasons. Constructing hyperkähler manifolds is not trivial. And I mean, if you have a conjecture about hyperkähler manifolds, you might want to test them on K3 surfaces first. No, but I just chose to have this definition. I'm not going to need this. It's just because I wanted to replace now, just to say a few words, that if I replace here 2 times 2 by 2 times n, and then you replace SU2 by SUn, and forget about this now, because now this becomes different, then this is the definition of a Calabi-Yau n-fold. So a K3 surface is a Calabi-Yau two-fold. So Calabi-Yau's. So some words about this, and I don't want to waste time, but I want to give you some words about the connection of K3 surfaces with M24 that dates back to work of Mukai. And right, so all of them are diffeomorphic. All of them are diffeomorphic. All of them have the following Hodge diamond. Right, so they're self-mirror in some sense. Yeah, I probably should write the zeros as well. And at least I want to give you one example, which is the only example we need of such a surface. As follows, just look inside of CP3 and look at the zeros of a polynomial, a homogeneous polynomial of degree 4. So if you're very unlucky, this guy is going to be singular, but if just move a little bit the coefficients, it's going to be a smooth surface, and that smooth surface is going to be a K3 surface. In particular, I mean, another example, which is also going to be in this form, is to look at a surface which is a 4-to-1 covering of P2 ramified along a quartic. Ramified over K. So an example of this is as follows. You look at the zeros. You look at the zeros of x y cubed plus y z cubed plus z x cubed plus t to the fourth is equal to 0. So that's a surface inside of CP3. These are the 4 homogeneous coordinates of CP3. And you map this to P2 to the coordinates x, y, z. Right? So if this guy, which is my Klein's quartic, if this polynomial is not 0, then there's 4 solutions to that equation. T to the fourth should be a non-zero number. And this guy is ramified whenever this is 0. Right? So this is a covering of P2, 4-to-1 generically, and ramified over a Klein's quartic. So, and it's also the set of zeros in CP3 of a polynomial of degree 4, so this is also a K3. All right, so why am I giving this example? Because this is a K3 surface that inside of its automorphism group actually is equal, but the automorphisms of this K3 surface, with an extra condition that I mention in a second, of this surface, I will call this surface X, is PSL2 over F7. So let me tell you what kind of automorphism, because this is the genius work of Mukai. So Mukai said, okay, so let's look at automorphisms of K3 surfaces preserving this holomorphic volume form, which is a symplectic form on a surface. So let's look at all symplectomorphisms of K3 surfaces. He classified all these groups, all these automorphism groups preserving the symplectic structure, they all live inside of M24. They're all subgroups of M24. Actually, he wrote down a list. If I remember correctly, these are 9 possible groups. Take that with a grain of salt. And this group here is the smallest one in that list. This is the smallest automorphism group for a symplectomorphism group for a K3 surface. But they're all classified and they all fit inside of M24. Each one of them is inside of an M23, but if you want to have them all inside of one group, it should be M24. So that's the first connection of K3 surfaces with M24, but actually these are all different than M24, so I can never find M24 acting on a K3 preserving the symplectic structure. So that's work of Mukai. I should probably write that. This is work of Mukai. The classification of the symplectomorphisms of K3 surfaces. But this K3 surface in particular has this group as automorphism group. I mean, it's easy to find this, that this guy acts there because you just extend the representation, the 3-dimensional representation, to having it act trivially on this coordinate, and now this group acts on this surface. Right? The polynomial is invariant by the action of PSL2 or F7. All right, so now I'm going to construct a beast where I want this group M24 to act. I should write down now the conjecture again, because that's the very first piece of the conjecture that I'm going to end up writing today. All right, so let X be a complex manifold. It can be even an almost complex manifold. Okay, what I'm going to write is going to sound like it's a beast, but I'm going to write down a bigraded bundle, an infinite dimensional bundle. It's going to be bigraded, but each graded component is going to be a finite rank vector bundle on X. And I'll do this in the following way. So let's fix K to be a positive integer. And I'll start with, let's say, T is the holomorphic tangent bundle. And T star is going to be its dual. So let's take this exterior algebra of T star, and let's put T star in bidegrees K1. Right? So 2 forms will have bidegrees 2K, 2. Let's tensor this guy with the exterior algebra of T in bidegrees K plus 1, minus 1. The symmetric algebra of T star in bidegrees K plus 1, 0, and the symmetric algebra on T in bidegrees K plus 1, 0. So for the physicist, I guess, I'm going to be referring to this first bidegree K as energy or conformal weight, and the other one as charge. So the half non-trivial charge are going to be my fermions. These guys are going to be my bosons. And now I'm going to make this into an actual beast by taking the tensor product over all k's bigger or equal than 0.
So what is the meaning of K again? So it just means
Several copies of the same bundle. Several copies of the same thing. It's just that now the degrees are different in this beast. I'm sorry? One is charge. So this gives me, this K and 1 give me a bidegree for this T star. So a section of this T star will have degree K for the first grading and degree 1 for the second grading. All copies of this bundle will have those 2 bidegrees. So if you look at 2 forms, which is a section of here, we'll have the first grading will be 2K and the second grading will be 2. the other, so a section of T here, I'm declaring the by degree of that section to be K plus 1 minus 1. And all of these here will have by degree, the second component of the by degree will be all 0.
My question was somehow, does it have anything to do with the grading on the exterior algebra itself? So is this
No.
K1
No.
the degree of only just T star, or is it the degree of the whole exterior?
It's only the degree of T star.
So and then extended to the grading.
Then you extend it to the whole, that's why I'm saying two forms should have by degree 2K and 2. Right? And that gives you a degree on the whole, or by degree on the whole beast here, and then you obtain a by degree by taking tensor products. And this I will call L of X, and this is a direct sum of L, Kj, and these are actual, I guess, yeah, I'll call it Kj. So this is a direct sum of Lkj, where Lkj is the by degree K, J component of that infinite dimensional bundle. But this is a finite dimensional rank bundle. It's a finite rank bundle. Vector bundle, holomorphic vector bundle over a K3 compact manifold. So I can take this cohomology. So I can write down a vector space, which would be, it's going to be a super vector space, which is the direct sum of Vkj, which I declare to be, these are all finite dimensional vector spaces because my manifold is compact, of X on L Kj. I mean, given Michel's lecture yesterday, I should have written down what is the characteristic series for this genus that I'm going to write, but I forget. And whenever I have a vector space which has a bigrading, right, by finite dimensional pieces, then I can take its graded dimension. And I will define L, Q, Y as the sum over all Kj of the super dimension of Vkj times Q to the K, Y to the J. Here, super dimension means the following. This is the full cohomology of this bundle. So I'll declare even, the even cohomology, and odd, the odd cohomology. So things in H1 would go with a minus in that sum. And now you just multiply just to correct by minus the dimension of X over 2. And the theorem, I'm going to give Borisov and Liebkover as reference, I guess. Because they wrote this down in connection to a vertex operator algebra, which is what I'm interested in, is that if X is a Calabi-Yau manifold, in particular if X is a K3, then if you write down Q as e to the 2 pi I tau and Y as e to the 2 pi I Z, then this guy converges. Qy is a holomorphic function, is holomorphic on the upper half plane times C. Tau is in the upper half plane. This is called the elliptic genus of X. This is two-variable elliptic genus of X. Actually, I'm going to mention something because these things appeared in Minoru's talk. They also prove that this is a Jacobi form this is a Jacobi form, a weak Jacobi form, of weight 0 and index the dimension of X over 2. And this just means for us that they have some modular properties when you act by SL2Z on the variables tau and Z. We're not going to need this. I guess what all right, so okay, so again for physics, I guess this is at least as a vector space. This is the space, the algebra of observables of the sigma model we target your manifold X. For the vertex algebra people, this would be, the vectors, as a vector space, would be if you take a BC beta gamma system based on T. Right? So these are your bosons, so you have your beta and gamma, and these are your fermions, so you have your B's and C's. And this is a vector space. This is that vertex algebra of free fermions. A tensor product of free fermions and a tensor product of free bosons. Actually, yeah, I'll mention this. So V, I'm lying this, and I'll say exactly the statement in a second, but V is naturally a vertex operator algebra. This natural vertex operator algebra called the chiral, the RAM complex of X. So this is a vertex operator algebra that Malikov, Shexman, and Weintraub introduced to any manifold, any smooth manifold, and in particular, it has this as a vector space. Now let me make the precise statement. That vertex algebra there has a filtration, and its associated gradient is this guy. But that's a technical condition. But as a vector space, at least, you have an isomorphism between these guys. Okay, so now the statement is as follows. That algebra, that vector space, that vertex algebra, has an action of the n equals 4 superconformally algebra. So that's a theorem, and now I want to give some names about that. Theorem. This V has a natural action of the n equals 4 superconformal algebra of central charge well, is 3 over 2 times the dimension of X, which is 4, so that's 6.
So this is only for A3 surface, or is it for any?
Thank you. That's a good question. So this is true for any hyperkähler manifold, and in particular, that charge 6 is for X being a K3 surface. Here, X is K3. This theorem is, on the one hand, is obvious to any physicist because they just say, oh yeah, okay, this K3 has n equals 4 supersymmetry. At the classical level, this was written down by Tamanoi in a book where he just writes this action on these bundles. And at the quantum level, actually, it's as a statement of n equals 4 vertex algebra being inside of the Carrel-Round complex of X. This is not written down, but it's an easy consequence of two works. One, because here is the cohomology of the complex, Carrel-Round complex, the holomorphic Carrel-Round complex. So this is a consequence of a work of David Bensby, Matt Chesney, which of course I'm going to forget how to write, Chesney, and myself in 2006. And myself alone in 2010, no, 2008. So a combination of these two works prove that there's an actual action of the n equals 4 vertex algebra on this vertex algebra there. But it's interesting that I think for every physicist this is absolutely trivial, but I don't know any other proof than just doing an actual long computation of vertex algebras.
So initial action means that this isn't the same as just the homomorphism.
Right. There's an embedding of n equals 4 vertex algebras inside of this as a vertex algebra. Yeah, and you just produce global sections that actually satisfy the right OPEs.
And is it just a statement of cohomology, or is there some statement just before the cohomology?
This, oh, well, the statement in the smooth level, so if you look at the smooth category, is that you have at the level of sheaves of vertex algebras two commute in n equals 4s. But if you want to get only one on the cohomology of the holomorphic one, you need to take the cohomology. So this is a statement really about the cohomology. It's a global statement. It's not a local statement. But you prove this by using the smooth two commuting ones, one in the holomorphic side and the other one in the anti-holomorphic one. I don't think it's an entirely trivial statement, but this is an easy consequence of these two works.
So there's no algebraic proof of this? There's no proof of this which doesn't appeal to the smooth category?
That's a good question. Let me answer this let me answer this later. I'm not sure. I'm not sure. I mean, for all of these K3s, well, no, I'm not sure. You can prove this algebraically for some things, like sections inside of a toric variety using bodies of results, and that you can do completely algebraically. I'm not sure. I have to think about how to do that. Yeah, as of now, I can only prove this using the smooth results. But the smooth result is formal anyway. Well, it doesn't. All right, so, okay, so the statement is that this n equals 4 algebra acts there. And I want to tell you why it acts. At least I want you to give a feeling as to why this Lie algebra acts. And this Lie algebra was included in Minoru's talk. So let me describe what this n equals 4 Lie algebra is. So the first line there, you recognize. That's a Virasoro Lie algebra. The second line should be, so inside of n equals 4, I'm going to have a bunch of Lie algebras. I'm going to have the Virasoro. Right? So this is this L series. I'm going to have this J's that is an SU, well, let me write SL2 hat. Right? These are the J's. Let me write this as SU2 hat. These are the J's. And the third line there just says that this Virasoro acts in the usual way as derivations. Okay, to that Lie algebra, let's add. Right, so there's many generators there. And this C here, I'm going to be looking at a representation where C is going to be replaced by 6. All right. Oh. I'm sorry? Oh, yeah. Yeah, that's certainly a misprint. Apologize for that. Yeah, that should be a minus. All right, so now I'm going to add the super part. That was the even part of the Lie algebra. So now, in order to add the super part, what I'll do is the following. You take two representations of dimension 2 of this Lie algebra, complex dimension 2 of this Lie algebra. These are this G plus or minus is a basis, and G bar plus or minus a basis. And this extends to, I'm sorry, the dimension 2 of the SU2, not of the SU2 hat. And now you just extend this to a representation of SU2 hat. So that's what's written down in this second line. So you have 4 set of generators now, which are these 4 fermions, where this SU2 acts, and the Virasoro acts in this way. This means that these G's are of conformal weight 3/2. All right, and now I need to tell you what is the bracket between the G's. And that's non-trivial, but I'll just write something. But, I mean, you don't need to remember this formula. You need to remember what it means. So this is just how they commute these G's. But let me tell you what's the connection to geometry, at least. On a Kähler manifold, on a hyperkähler manifold, you have, I'm going to think of this as the Laplacian. Actually, L0 will be the Laplacian of the manifold. I'm going to think of the 3 J's as the complex structures. Forget the subindices M. So I'm thinking of the 3 J's as the complex structures, and forget the subindices M for a second. And the 4 guys here, if instead of thinking in SU2, you think in SL2, that singles out a single complex structure, and these 4 guys can be del star, del bar, and del bar star. And what you know is that the commutator between these 2 guys is the Laplacian, and the commutator between these 2 guys is the Laplacian, which are the Kähler identities. And this is more or less what's written down there. That the commutator of 2 G's should give you the Virasoro as the Laplacian. You can actually make this statement somehow precise, but this will be enough to give a feeling as to why this Lie algebra acts here. The J acts really they act really as endomorphisms of each of these bundles. The subindex M, the only thing that does is just move from one copy of T to the next copy of T in a different degree. You have many copies of the same bundles. And then the other operators act as I just mentioned. So the L acts as the Laplacian, and this G plus and G minus act as the del bar and del stars. So that's more or less the idea as to how you would prove that the action of n equals 4 in this algebra. All right, so now I can actually write down the conjecture, but now I should mention people that actually worked on this conjecture, not as myself. So this is my phrasing of this conjecture. It's not exactly how it came, but I'll explain how this came. This came from work of Eguchi. This is what started the whole thing. Oguri and Tachikawa, 2010. I'll explain what they worked in a second. Then Miranda Cheng, Duncan, and Harvey did some work about modular forms related to this conjecture. And I'll also mention Gaberdiel, Volpato, and collaborators. And I'll mention, I guess, Catherine Wendell and collaborators. All right, so there's a lot of numerical evidence to the conjecture I'm going to state, and there's even evidence against this conjecture, as I'm going to phrase it in a second. Yeah, it's interesting, but I need to distill that evidence against. Anyhow, so the conjecture is as follows, is conjecture. There exists a natural action of M24 in V. I'm going to ask it to be by automorphisms of the vertex algebra. That's not how it appears. Commuting with n equals 4. As stated, this conjecture is obviously true. It acts by the trivial action, works. Right? But I want to say why this should be a non-trivial action. We could have phrased a much stronger conjecture. Just take the commutant of n equals 4 inside of that vertex algebra and ask it to be M24. But let me tell you how. Yeah. It is the chiral rank complex of X, whose associated gradient is this. That's correct. But all you need to know to guess this conjecture happened at the associated gradient. That's why I want to mention this. So why is it? How does this conjecture come from? It goes as follows. I said this elliptic genus, this generating series for the dimensions, is a weak Jacobi form of weight 0 and index 1. Right? The dimension is 2. There's only one such function. It's very well known. It's a product of theta functions. So there's only one Jacobi form of weight 0 and index 1. Now we know that there's an action of n equals 4 on that vector space. The characters of those representations that appear inside of n equals 4, they're very well known. So you can decompose this L of Q, Y, into sums of, say, AN, and then the character of the nth representation of n equals 4 appearing there. And ANs are just the multiplicities of those representations. And this is a problem about decomposing, writing a function that is well known as a linear combination of other functions that we know. Sorry? Sorry, I didn't understand the question. Yeah, we have the two variables. Why? No, in AN, no. No, in AN, no. No, you just have the characters. So this means just how many times this representation appears inside of it. And the observation they make is, and I'm hiding also the fact that I'm ordering the representations of n equals 4 by one number, one integer number. And the statement they made is that these numbers, ANs, that appear are as follows. So the ANs are, the first one is 2 times 24. The second one is 2 times 45. The third one is 2 times, I think it's 231, if I'm not wrong. Take this one with salt. And the fourth one is also twice a dimension. Someone observed that these are always 2 times the dimension of irreducible representations of M24, except for this one. The permutation representation is not irreducible. It should be 23 here. But you can explain this. But the rest of the series, they're always either irreducible representations of M24, dimensions of those, or you can write them as sums of those numbers. So therefore, the conjecture. Okay, so then there should be an action of M24 that explains this. And the connection, and that's why Cheng, Duncan, and Harvey started working on this, is that if you take the sum of an q to the n, now this is a mock modular form. As, again, taking out this first guy there, as Minoru stock, in the same sense as Minoru stock. Okay, so let me just, the last 5 minutes. This is incredible. This paper appeared in 2010, I think 3 months, and this is just a statement. They weren't even looking at M24. What they were doing is, Eguchi and Oguri, they've been doing this for a while. They had already done this for the n equals 2 vertex algebra, where you take a huge vertex algebra and you write down the character as a irreducible representation of n equals 2. And when they did this for n equals, and they also found in that case mock modular forms as the generating series for the multiplicities. And in the n equals 4 case, well, this observation appeared, and immediately, I think 3 months later, they put this in a computer and they checked that up to the 10,000 coefficient. This is the numerology I say. You can always express this guy as sums of irreducible representations of n equals 4. Then they computed the Thomson series. They have the twisted characters. They're all consistent in that sense. All right, so let me tell you what is the first piece, which is the conjecture I wrote of this conjecture. I mean, this is a huge, huge beast. But now, in this vertex algebra, you can ask, on the vertex algebra V, the Carrel rank complex of X, you can ask, what is the component that has conformal weight 1? And it turns out that that space, the conformal weight 1 inside of V, in that by degree would be k is equal to 1. The only thing that survives is h1 of x with values in the endomorphism value, in the endomorphisms of tx. Now, if you look at h1 of a bundle, that should be the tangent bundle to some moduli space. And indeed, this is a very well-studied moduli space. You look at M to be the moduli space of deformations of Tx as sheaves. Mukai studied this manifold. Mukai did a lot of work on these things for K3. And this is a holomorphic symplectic manifold. This is a K3 manifold that has dimension 90 and is symplectic. Holomorphic symplectic in the sense as Sasha's stock. So, okay, so this naturally is, you can write this naturally as, oops, I'm sorry. Now, if I look at the tangent bundle at Tx, which is a point in that moduli space, 2M, the tangent space at that point, this is a complex vector space of dimension 90 that is symplectic. So this is naturally C45 plus C45. There's a natural isomorphism there. And M24 has only 2 representations that are of dimension 45. This is the second irreducible representation of M24, has dimension 45, and it's 1 and its complex conjugate. So the conjecture would imply, in particular, that M24 acts by that representation on that space. This is the very, very first non-trivial case of that conjecture, and it already involves M24 acting on this tangent space. I mean, you can even ask whether or not it would act on that moduli space. That I won't expect. But it's already interesting to see M24 in connection to deformations of the tangent bundle of K3. And this is very, very first non-trivial case of that conjecture. And okay, so that's about all I wanted to say here.